Okay, so today I'm going to walk through how to solve the contest problems at the end of chapter 1. I think these are the most fun and most interesting problems in the chapter. So the first problem says this. Jim knows that x is an integer greater than 2 and less than 8. Remember that this z means integer. Okay, and Kim knows x is an integer less than 9 and greater than 4. And Tim knows that x is an integer greater than or equal to 2 and less than or equal to 6. And then the question asks, how many possible values are there for x? Okay, so the first thing that I'm going to do is translate each of these expressions into inequalities, right? So Jim knows that x is greater than 2. So x is greater than 2 is the same as 2 is less than x. And x is less than 8. So Jim knows that x is between 2 and 8. Kim knows that x is less than 9 and greater than 4. And finally, Tim knows that x is greater than or equal to 2 and less than or equal to 6. Okay. So I'm going to draw on the number line what each of these inequalities are telling us about x. And really, I'm going to use blue for Jim. Okay, so we know that x is bigger than 2, so x is an integer, so x could be 3, 4, 5, 6, or 7, right? It's less than 8, so it can't be 8 or anything that's bigger than 8. I'm going to use red for Kim. So from Kim, we know that x is bigger than 4 and less than 9. So that means, that means x could be 5, x could be 6, 7, or 8. And then from Tim, we know that x is between 2 and 6. So Tim knows x is between 2 and 6. So, and it's also could be 2 because it's 2 is less than or equal to x, or x is greater than or equal to 2. It could be 3. It could be 4, 5, or 6, because x is less than or equal to 6, so x could be equal to 6. Now, if we take a look at the overlap between all of these, we see that there are only these two possible values that x could be. X could be 5, or it could be 6. And that's our answer. Actually, I'm sorry, that's not quite our answer, because this is asking how many possible values. So 2 possible values for x that satisfy those constraints from Jim, Kim, and Tim. Okay, let's do the next problem. So the next problem says, starting with a certain number, Jane divided by 2 and then divided by 3. Her answer was 1 out of 15. Or 1/15. However, she should have multiplied by 2 and then multiplied by 3. What is the correct answer? Right, so Jane followed one procedure. She took some number and she divided by 2 and then divided by 3. So really she divided by 6, right? And then what she really should have done is multiply by 2 and then multiply by 3. So she should have multiplied by 6. All right, so what happened was Jane was given some number and she did something. And then out popped 1 out of 15. And the something that she did was divide by 6, right? Because x over 2 divided by 3 is really x over 2 times 1 over 3, which is x over 6. Okay, so that's a little side note there. So in order to find the correct answer, we need to figure out what this x is so that we can apply the correct procedure to x. And we can figure out what that x is by doing the reverse of what Jane did, right? Or rather, we will solve for x in the equation x divided by 6 equals 15, right? So that tells me that x equals 6 over 15, which also tells me that x equals, right, because 6 and 15 are both divisible by 3, so x equals 2 out of 5. So this is what Jane did as her something. What we want to do as our something is multiply by 6. So we're going to take this x and apply the correct procedure, which is multiply by 6, and then we're going to see what that answer is. So 2/5 times 6 is going to be 12 over 5. And that is what the correct answer should have been. Okay. Number 3 is let A, B, and C be positive real numbers. Okay, remember that this funny R is for real numbers, and this is for the positive ones. So we have, if A times B equals 48, and B times C equals 96, and A times C equals 72, what is the value for A, B, C? Okay, so we know that the value for A, B, C is going to be A, B times C, which means, we know that AB is 48. We can substitute that in here, and now we know it's 48C. And that kind of helps us, maybe, because all we really need to do is figure out what this C is. The problem is that we don't have C by itself. We have B times C and we have A times C, but we have no C all by itself, right? However, if B times C equals 96 and A times C equals 72, then we could express C in terms of B and A. So C is going to be, from the top one, it's going to be 96 over B. And from the bottom one, it's going to be 72 over A. Okay. Both of these are C equals something, and C always equals itself. So this tells me that 96 over B equals 72 over A. Which means that this means that 96A equals 72B, right? Where over here I multiplied B times B. Sorry, that is not what I did. I don't know why I just wrote that. I just multiplied with B and B like this. this became 1, this became 72b over a, and then I multiplied with a times a on both sides, and that's how I get 96a equals 72b. So this means that 96 over 72 equals 96 over 72 A equals B. And furthermore, I know that A times B equals 48. So I can substitute this value, this 96 over 72a, into this expression over here where the b is, right? If you recall the substitution principle from earlier in this chapter, if I substitute in something that means the same thing as something, then it doesn't change my it doesn't change my equation, right? So when I substitute that in, I get a times 96 over 72 times a equals 48. It looks a little bit ugly, but we can simplify it a bit. And I'm going to move it over here like this. So when I simplify this, I wind up with a squared, right? A times 96 over 72 times a squared equals 48 over 96 times 72, right? Because I brought this 96 over 72 over to this side, which means I'm multiplying with the inverse, which is 48 over 96. Now, 48 over 96 is actually just 1/2, right? 48 times 2 is going to be 96 times 72. Well, half of 72 is 36. So this tells me I've got a squared equals 36, a equals 6. Okay, now I'm getting somewhere. A equals 6, a times b equals 48, so that means that b equals 48 divided by 6, which is 8. So I've got b equals 8. And c equals 72 divided by a, which is 12, right? A was 6. 72 divided by 6 is 12. So I have really, I just need to do 48 times 12, right? ABC is going to be 8 times 6, which we already established was this 48 times 12. I don't know what that is off the top of my head, but we do know that 48 times 2 is 96. So this is really 96 times 6, which is 6 by 6 is 36. And then 6 times 9 is 54, plus 3 gives me 576. So my final answer, and I don't have any room for it really, is going to be A, B, C. Well, let's do it over here. A, B, C equals 576. And then I don't want there to be any confusion on what the answer is. So I don't want anything else that looks kind of boxed-ish, right? So this is a really good example of why we box our answers. It's so that when we look at a problem where we've done a lot of work, we can clearly see what the answer is. Although generally the boxed answer is going to be at the bottom. It's not going to be this super messy thing. Okay. So the last problem is let X be an element of the set 1, 2, 3, up through 20. For how many values of X will the value of the expression (3 plus x over 5 plus 12 over x) be an integer? Okay, the easiest way of doing this is to just enumerate the possibilities. So we say x is my input, and I'm going to have this expression. I'm going to call it star so I don't have to rewrite it. Star, and then I'm going to say, is this an integer? Question mark. So I've got the possible input 1, and that's gonna, star is gonna evaluate to 3 plus x, x is 1, so that's gonna be 4/5 plus 12 over 1, just gives me 12, and no, that's not gonna be an integer. If I put 2 as an input, now I get 3 plus x as 5 divided by 5 is 1, plus 12 divided by 2 is 6, so that's going to be 7. That is an integer. 3 is going to be 6/5 plus 12/3 is going to be 4, and that will not be an integer, right? So what we're finding is the integers are happening, or we've only had one so far, but it's really happening when both of these expressions are evaluating to an integer. So So star is an integer when that expression on the left, the 3 plus x over 5 is an integer, and 12 over x is also an integer. Okay, let's keep going. Oops. If x is 4, this is going to be 7/5 plus 3. So that doesn't work out for us. And now we really see that so maybe this is 1 is kind of like this, 2 is kind of like when one of A or B I guess what I want to say is when exactly one of A or B is an integer, star is not going to be. Right? Because here, this is A, this is B. Here, B was an integer in both of these cases, but because A is not, these cannot be integers. Okay, that's really interesting. If we look at 5 as an input, then we have 8/5 plus 12/5. Now, this is a really interesting case because it's actually 20/5, which equals 4. So this is an integer. So now we have the case where another observation. Let's see where to put our other observation. So somehow this is like when A and B are compensating for each other. Right? In the sense that A was 8/5 and B was 12/5, and still they were able to come together and make an integer. And this condition is really the most challenging one to figure out when that's going to be the case. My intuition is that it's going to be the case for inputs that are multiples of 5. But I'm not going to go down that path of trying to verify that or prove or disprove that in the interest of time. Okay, so let's go back to our inputs. Now we input 6, and when we do this, we just get to increment this numerator here, right? We've increased x by 1, so we'll increase that numerator by 1, right? This will be 9/5 plus, and then we're increasing the denominator here by 1, plus 12/6. So let's see what that is. 9/5 plus 12/6. Well, this is, oh, sorry, I didn't finish writing out the observation 2. Star is not an integer. So in this case, our observation 2 is going to apply, right? Because 12/6 is going to be 2, but it's the only one that's an integer, so this is going to be a no. Okay. Let's continue on the next page. So now we're going to have x here. We have star here. Our integer check. And we're on 7. I believe, yes, 7. So this is going to be, let me write the expression so we are reminded. Whoops. 3 plus x over 5 plus 12 over x. This is star. And then I want to copy our observations over so we don't lose track of those. Let's see, copy. whoops. And then here are our observations so far. Okay. So 7 goes in, and then we have 10/5, which is 2, plus 12/7, and this is going to be a no because of observation 2. So I'm going to make a note of that. 8, 9. All right. And then for 8, it's going to be 11/5 plus 12/8, which is going to be 3/2, right? 11/5 plus 3/2, that's going to be 22 plus 15/10, and that is certainly not going to be divisible by 10, right? Because we're going to wind up with this like 37 on the top, so that's bad news bears. So this is kind of the opposite of 3, right? They were both fractions and couldn't compensate for each other. Okay, this will be 12/5, and I'm just going to write all of these out quickly, where if you remember, we're just incrementing the numerator by 1 every time. Okay. And then on the other side, we're just incrementing the denominator by 1 every time. So this was 12/8. Now this will be 12/9, 10, 11. This will be 1. Ooh, I see an integer. This follows observation number 1, where both of these expressions evaluated to integers. Okay, 12/13. And then I'm just going to write 19 and 20 over here. All right, and then we would want to check if each of these expressions that we have evaluates to an integer or not. And I can tell you that would be very tedious. So why don't we first take a look at this one, this 4 plus 12/17. Well, that looks a lot like our observation 2, right? Where exactly one of them is an integer and the other one is not. So we won't be able to get an integer out of that. And then what you would want to do is evaluate the rest of these. I wrote a little script that did it for me, and I can tell you that actually none of these wind up being integers. In fact, the next integer comes when x equals 30. That might be a fun thing to verify. So 3x plus 5 is going to give me 3 plus x, where x is 30, is going to give me 33 over 5 plus 12 over 30. And this is going to be, so 12 over 30 is going to be 6 over 15. Those are also both divisible by 3, right? It's 2 over 5. Plus 33 over 5 is going to be 35 over 5, which equals 7. Well, this is a little bit juicy because over here, this one was also equal to 7. Over here, this was 4, and this was also 4. That's kind of an interesting pattern to me. Something that would be interesting to investigate further, but not something I'm going to investigate further right now. Let's just finish up the problem. So the question was, for how many values of x will the value of the expression be an integer? And we found where x is restricted to this domain here, we found this value for x. Oh, I did the wrong thing there. We found this value for x, this value for x, and this value for x. So that's 3 of them. 3 values for x, and they are x's in the set 2, 5, and 12. And that is my answer. Which, you know, if I were writing this out, it would go at the end of all of my work. But I'm kind of out of room on this page, and I don't want to start a new page just to write that answer. Okay, that's it for the contest problems. What I think would be a good idea is your book has a chapter summary at the end of the chapter, and it goes through 8 key points of the book. It'd be a good idea to read through those. And then there are chapter review problems where on the right side of each problem, it makes a note of which section corresponds to the problem, or like which section that problem's material corresponds to. And those are multiple choice questions that I think, you know, should be relatively quick to go through. And then I think it would be a really good idea to try to take the chapter test, just to, you know, try to solidify the material before moving on to the next chapter. Okay, that's it for this lesson.